has a payload which was, I think, 26 kilogram, and the mass of the payload plus the mass of the air inside the balloon has to be the same as the mass of the air which was displaced by the balloon. That is how an air balloon works. It displaces cold air with hot air, and the hot air is lighter, and so it can carry something. Okay. So in class, we did look at that the masses of air can be written as the density of the air times the volume, which is the volume of the balloon. And that is the density then outside of the air, outside of the balloon, determines how much was displaced times the volume. Okay. So we have right away a formula that the mass of the payload divided by the density on the outside minus the density on the inside, and that is the volume. So we know already this quickly what the volume is, just we don't have the number. So I brought this one here over to the side, then I have the volume times the row inside minus row outside, and then I divide that and I have the volume. Okay? So now I know what the volume of my balloon is, except that I still don't know quite what the density of the air inside and outside is. So really I do know what the density of the air inside and outside is. Because I know that for each of these densities, that is the mass of the payload divided by the density is the number of moles I have outside in the volume which was displaced by the balloon times the molar mass of air divided by the volume of that balloon minus the number of moles I have inside of the balloon times the molar mass of air, which is the same thing, divided by the volume of that balloon. We did that kind of in class already when we would look at the barometric formula. Okay, so again, same thing we did in the barometric formula, PV equals nRT. So I know N over V equals P over RT. So I can put this in here. So that is the mass of the payload divided by the molar mass, which is of those sides, and then molar mass times the P, the pressure. The pressure is always the same, correct? But air balloon is not as a hole in the bottom, and the same pressure as outside, otherwise air would go in and out, and to some degree air does go in and out. So the pressure is something which is the same everywhere, and then I need to divide it by R times, and that is the temperature inside, that's the temperature outside of the balloon, we are outside here, and minus here the molar mass of air times the pressure, there's only one of them, divided by R and the temperature inside of the balloon. Okay, so that is the R times the mass of the payload. The R was in the denominator over here, is divided by the molar mass of air, that's everywhere as well, and then the whole thing needs to be divided by P still, we didn't figure that out what the P is, and 1 over the temperature outside minus 1 over the temperature inside. Okay, the P we know from the barometric formula, P is P naught times e to the power of m minus m molar mass of air times the gravitational constant times the height divided by r, the gas constant, if the molar mass is, and if the molar mass over here is grams per mole, and divided by the temperature. The temperature is, of course, the temperature outside, which determines the pressure. How high, what the pressure is at a certain altitude doesn't depend on how warm the balloon is. It depends only on the outside temperature. So it's T outside over here. Okay, then you can plug this one here in, and you have R times the mass of the payload divided by the molar mass, and here you have P naught, the standard pressure, which you had at ground level, times e to the power of minus the molar mass, g, the gravitational constant, height, the 10 kilometers it was flying at, divided by r, temperature on the outside, and then 1 over outside, 1 over 200 Kelvin over here, minus 1 over 240 Kelvin. Pressure inside, the temperature inside. And of course, 1 over 200 is a bigger number than 1 over 240. So this is a positive number. Some of them are negative. Okay, and then you just plug the numbers, and you get on the order of hundreds of cubic feet. That is on the order of the size of this room, right? It's about 10 meters this way, it's about 10 meters that way. That would give us 100 square meters. It's about 4 meters tall over here, so this room would be about 400 cubic meters. So on that size, the balloon is. Meaning it is quite a bit smaller than those balloons which you see carrying people. They carry not 26 kilograms, but they 26 kilograms a third of a person. But a couple of people, so probably 10 times as much or so, 20 times as much. But then also don't fly quite as high because the 10 kilometer altitude you have the air pressure, which is just a 0.2 or so of what we have. So then you can go to that. So does it make sense? Yep.
You said for the barometric wave, you said you use the outside light.
The outside temperature?
Yes.
Because how the pressure changes in the atmosphere does not depend on how warm it happens to be in the balloon.
Oh, right.
It only happens to how warm is the air outside. So, okay, good. Then I did not put new slides up. I did not print up new slides because there isn't really much in terms of new slides. Because we are going to do really what we had on the slides the last time. There's homework today, and the homework today will be to reproduce what I'm doing here in class in Excel, and using a slightly different policy. So in this class, we are going today study a made-up problem, completely made up, which allows us to understand a little bit how internal energy and entropy and so on work in terms of statistical mechanics. I would like to study a quaterniform molecule, like this one here over here. And so just 4 benzene rings after another. And what I want to investigate in particular about that molecule is its rotational conformance. And if you have a molecule like this, flat, then there is steric hindrance between these 2 hydrogen atoms and these 2 hydrogen atoms if the rings were flat. But if you rotate the rings like this, then there's no steric hindrance between the hydrogens anymore. If you take the ring this way, then these are far away from each other. So it's energetically favorable for these molecules to have alternating planes for the rings, and not the rings in the same way. But it's not a big energetic penalty. It is an energetic penalty, but they can rotate around, so it's not a humongous energetic penalty. And I just made up over here the number, which is in the right ballpark, but which I change every year between the classes so that there's copying target. Which that is 40 millielectron volts. It's not the right number. But so for every time that I have a pair over here of molecules, of rings, which are in plane, there is an energetic penalty to be paid of 40 millielectron volts, or 0.04 electron volts. That's just assumed. And that is what I'm going to use in class here. In your homework, the molecule is a little bit different, has one fluorine atom substituted over here. And where if the fluorine atom were to be here in steric hindrance, then it would be not be 40 but 80 millielectron volts. So just a little bit different, that you have to think of it a little bit new and what you do at home and what we did over here. So I would like to study the conformations of this molecule and figure out what is the internal energy of those conformations. And then what is the entropy associated with those conformations? What's the probabilities of those conformations to occur, and so on and so forth, using Excel. Because I think that gives us a good idea about how we need to work with these statistical mechanic approach. So, which was this kind of the average and this kind of way of looking at the functions. We looked at Z and we looked at U the last time. And in the course of what we're going to do, we will need to derive a little bit more here. So there will also be some work on the board, which you don't need to do. You only need to reproduce the Excel file. You don't need to do any derivation for your homework. You just need to reproduce what I get in the Excel. Okay, then let us try to get started. So I could get the Excel file only in as much as this, where I said, okay, I know what my Boltzmann constant is, and I know the electron volt, and I know the joule, and then I also know that the energy of my coplanar rings, that was 0.04 in electron volts, which gives me this value here in joules. Okay. How do I get started? First of all, I would like to give cells some names. It's really important often to organize your notebooks. And the first thing in the notebook in Excel, please note, I didn't use any of the columns on the left. I didn't use the top line. Please do the same. Please don't use the top row or the left column. UTAs will be happy about that because then they have a place to write something. And also, it's often nice to be able to go one more up or one more to the left, and you can't if you use them. The next thing is that I can do my calculations now either as I units or I can do them in electron volts. Both, of course, is fine. But I need to define what I'm really interested in. So I might want to do it this time in SI units. So maybe I want to use these two values to look at. In the end, as I said, it doesn't really make so much of a difference. But that being the case, I will use my Boltzmann many times. And so that I don't have problems with this, I define this cell over here. Now, if you were to work just by yourself, you would give it an appropriate name. Given that you're working here in the class, I would like you to give a personal prefix before that. So LB would be my initials. I will upload into iLearn personal prefixes for each one of you, and then I say this is KB. So now I defined that this cell here, which is D3, can also be referred to as LB underscore KB. I will upload them into Island for you. If you work in a group, one of you use the prefixes, please use them. The reason for why I'm asking you to use prefixes as I put them into the gradebook is that you might put many different homework solutions into one Excel file, and Excel would not like it if there were different, well, multiple definitions of the cell name. Especially if some of you work in electromos and others in Joule, it would completely mess up the whole Excel sheet. So please do use those person prefixes. And then here, that would be then the energy for the trees. Okay, so I define these. Good. The next thing is, I'm worried about this molecule with 4 rings, correct? So let's have one more look at this molecule. See how many configurations of that molecule are there. I'll first do that on the board, and then I'll type it into Excel. What about that? Just need an empty board. So, the ground state with 0 coplanar rings looks like this, correct? I have one ring this way, the next this way, the next this way, the next that way. Okay, everybody with that kind of shorthand which I'm writing over here. Your shorthand needs to be a little bit more complicated because you have that flow when you do your homework. But my shorthand is that simple. And this one here has clearly 0 coplanar pairs, the lowest energy state. How many ways are there to set up the molecule this way? There's only one in my case. Only one for my molecule. Because if I have that molecule, it's just whether I look this way at it, or from this side and so on. It's really only one state of the molecule, which has always alternating rings. The other things is just how, from which direction do you look at the molecule, and you could make them all the same. Now then there are ways of having one set of coplanar rings. For instance, I could think about having 2 rings like this and then this one. Now I have one pair of coplanar rings. I need to pay the energy price once, correct? How many ways are there to set that up? Now there is at least one more, which is kind of easy. This one, correct? Also one set of coplanar rings, and then otherwise there is. Now I could say, oh, this one here could be on this side. But that just means I'm looking from the opposite side of the molecule, whether it's left or right. I'm looking from the behind you, from the front. It's the same one. So it turns out that's really all ways of setting it up, that I have only one set of coplanar rings in my molecule. Your molecule might be different. I can have 2 coplanar rings in my molecule. I can have this one, for instance. Or I could have this one, also 2 sets of coplanar rings. And if you think about it again, these are the only 2 ways of setting it up to have 2 coplanar rings. All the other things is, are you looking from the left or from the right of the molecule, or from above, below, and so on and so forth. So they are the same molecule, just you looking differently. So from the perspective of the molecule, they are more. And then there's of course one set of setting it up with 3 coplanar rings. Having the whole molecule. And there's again only one. The one which had this one is just I'm looking from here or I'm looking this way. It's the same molecule. So the molecule doesn't change. So I have only 6 configurations. So I have 6 energetic states I need to worry about in the system. You understand the difference between gas theory, where we have an infinite number of states, infinite number of velocities the gas molecule can have. And here now in statistical mechanics, where we make a sum over all of our states. And in order to be able to make the sum over all of our states, it needs to be a countable number of states. And we just figured out, for the molecule I'm looking at, there are 6 states. So let's type them in. So here we have the state, this one here, and then we have the state, and we also had the state, and we had this state this way, and this, and finally we had the state this. Right? That were the 6 states which we had for our molecule, the same thing which you have on the board over there. And then over here we have 0 coplanar rings, and we have 1 coplanar ring, still 1 coplanar ring, 2 and 2, and here we have groups. So in order to keep track, this one here was a configuration, and this one here was number of coplanar rings, and then the energy of the system. Now the energy of the system, which is relevant for the configuration, is of course that number over here times the energy constant which I give the system. Okay? So I can immediately calculate what are the energies of those states. So now I know the energies for each one of these states. Okay, meaning I know something more. In order to know, learn something more about the molecule, it would be good to know what the canonical partition function for that molecule is. After all, we know canonical partition functions are really the important thing. If we have the canonical partition function as shown over there in the top, then many of the other properties will follow. So let's get the canonical partition function. In the canonical partition function, we have this minus Ej over Kt or so, right? So let's just say we have a row here. Oh, that's good. Where we put our temperatures. Okay, and if the temperature were to be maybe 100 Kelvin, then I can evaluate this e to the power of minus e over kt. So this one here would be then the exponential of minus the energy divided by, and I need to use my K Boltzmann, and also I need to multiply by the temperature. And then I get a value for that, and it's of course 1. E to the power of 0 is always 1. After all, the energy was 0. So then I would like to pull this down, but that doesn't quite work yet. Because if I were to pull it down, then this reference here slips, and I don't want this reference to slip. So what I need to do is I need to protect here for the row in which I'm interested to look at by using the dollar sign in front of the number 6. So now the 6 is protected and nothing will change with that 6. Okay, so I can calculate it, and at 100 Kelvin, this is 1, and those values here are all really, really swap. So now, what I calculated here was x of minus e over kt, correct? That is what I did in this column. So, if I wanted to know what my canonical partition function z were, then my canonical partition function z, that is the sum over those, isn't it? So now I have my canonical partition function for that system. I can find that right away. I'm really fine with that. So I immediately figured out what the canonical partition was. It becomes interesting as soon as we look at the temperature dependence of this canonical partition function. So let's have this not really only one temperature, and not maybe, let's start at low temperatures, let's start at 10 Kelvin over here, and let's say that this temperature is this one here times 1.3 or so, then I can have geometric series of my temperatures, and that might be a little too many for that. That goes beyond physical. Okay. Okay. Maybe. Okay. So now I'm looking at different temperatures. So now I would like to just move this over here, correct? But this still doesn't work really. It doesn't work because what I'm having over here now is that this reference here moves. I don't want to have this reference, which used to be the reference to the energy, that moves. So I need to protect the column of that reference. That was this one over here. I need to put my dollar sign in front of the D, that the column is protected. And then I can pull this over. And I can calculate it. Now that is all very trivial over here because it's still energy zero here for this molecule, so it is always e to the power of, it's always e to the power of 0. But if I go down with these ones here, then I'm getting some values which change. And then I can of course do the same thing here with my canonical partition function. And you see, the canonical partition function will change with temperature. So we can say that might be actually something to look at. So let's insert a graph and maybe points and for that graph we select the data and we put a new column in here, and the name of that column is that we are interested in the canonical partition function, and the x values here are the temperature values, and the y values for this one here are the canonical partition function. Okay, so we can see that the canonical partition function in our system first appears to be pretty flat. Nothing much happens when we are really cold temperatures. Nothing much happens at all. The molecule likely doesn't have enough energy to even get one coplanar pair. It's all in the ground state. And then something changes, and then it becomes flatter here again, as you can see. So something else is here, and at some point the answer for that would be that there's so much energy in the system that at those very high temperatures over here, it doesn't care about the energy associated with coplanar pairs anymore, and it's just random. But that is just my interpretation. We can actually look at that. Because we know that the probability for the system, the probability P, for the system J, for the system to be in state J, is e to the power of minus e of j over k Boltzmann times t divided by z. That was the probability for the system to be in state J. So we can see what is the probability for the molecule to be in a particular state. So let's come take these ones here again. And then we can calculate the probability. So the probabilities for this state over here equals the x over minus e over k Boltzmann times t, this one here. But we calculated that one already. That one was this. And the whole thing then needed to be divided by c, right? But we calculated our z. That was here, right? So we already figured out how to do that. Now I would like to pull that down for each of those states. Over here, but I have again this problem that something doesn't work right. Let's see what doesn't work right. So I can have a look, and then this z thing here is being pulled down. I don't want to have the z thing being pulled down. The z is always the same for each of the things. So over here, I need to protect that I stay in row 15, and then I'm good. And now I can do and take this, I think, over to the right hand side. Okay. So now we can directly have a look at what are those probabilities. So we can make our probability graph for that. And we insert the graph again in the same way. And then we select the data for this graph, and we add the data we are interested in. This molecule and the x-axis values are those over here, and the y-axis values are this one. And then maybe we are interested in another molecule, maybe the one of those which has one coplanar pair, the little pair over here, and then again the x-axis values. These ones here, and the y-axis values. These ones here, and we have, and then we can also say, oh, we might be interested in a molecule which has two coplanar pairs, maybe this one here, and for that the x-axis values are this one over here, and the y-axis values are those ones over here, and we have the, and finally, let's add to our graph also the molecule which has only coplanar pairs, and the x-axis values for these, and the y-axis values here. Okay. And let's make sure that there's Okay, good. So, what we find over here is that if we at low temperatures, then the molecule is all sitting in the ground state, in the state which has only one. So maybe we need actually a legend over here, you know. So it's only, pretty much only in that state. And then we come to a certain temperature, maybe over here or something, maybe 50 Kelvin, somewhere there. We come to a certain critical temperature at which the other states also get some population. And the molecule is not anymore in the ground state only, but also populates the other state. First, the state here, which has one coplanar pair, and then a little later and a little slower in the state which has two coplanar pairs, and finally in the highest energy state of the molecule, which has none. So that is what statistical mechanics tells us. And remember, we didn't really put any arcane knowledge in that, right? We only did some very fundamental math saying the states only depend on the energy. That's the mass. And we can come up with quite this. Okay. As a next step, we can ask ourselves, okay, what's the internal energy of our system? Okay, let's do internal energy. Let me slide this graph here over and look it to the side and form it away. And now I want to put the internal energy up here so that I have it. So let me make a little space over here. So I'm interested in internal energy U of my system. How do I do that? Now, there are two ways how I could get possibly to the internal energy, correct? I could use this one here, kT squared dln z by dt. That's problematic, of course, telling Excel how to make the first derivative of the logarithm of a value. Excel will not do it. But it's actually not so bad, because this one over here, that's way easier, correct? So with that, I can do it right away. So maybe I should have actually put my U underneath here. And then I know these are the probabilities, correct? Now, I also know about my number of coplanar rings or so I can just let me space over here. Okay, so I have my probabilities. I need my probabilities. The probability times the energy, right? That is what I need to make the sum. Okay. So that are my probabilities. Probabilities start here. Those are the energies still here start the probabilities to take over. So how do we get that energy? I need to make this sum, correct? But I need to make the sum of the product of the probability and the energy. Ah, easy. I use the sum product function. So I'm interested in energy, and then I want to multiply that with the probability. And I get the result. Now again, I would like to pull that, sorry, I would
like to pull this over to the side to look at what the energy is, but that will not work because the references will not work the right way. These were the energies, they always need to stay over here. So in order to keep my energy reference always to column D over here, what I need to do in this formula here is I need to protect my D's. So protect the D's. So I protect my D's. And now I can calculate what's the energy of each of the molecule at each of those temperatures. So, and I always like to graph things when I want to see. So, let's make the graph. And select the data. And at the data, I'm interested in internal energy, and that is here. And my temperatures are here. And my values I want to plot here. Okay, so now I figured out what is the internal energy of this molecule. And you see again, for the internal energy in the beginning, nothing much changes. The heat capacity of that system is pretty much zero, right? In order to make it warmer from 10 Kelvin to 20 Kelvin, I don't put almost any energy into it. It has a very, very low heat capacity. I don't need to put much energy into it. But then there's a critical temperature around here, maybe 150 somewhere Kelvin, and then it goes up. And then it is for a while pretty linear. Heat capacities like we like heat capacities, correct? Doesn't depend on temperature. The slope over here is kind of constant. And then in the end it flattens out. Which is very similar to the other curves which we saw already, which is, if we go to our other curves which we have over here, then it is somewhat related. It looks somewhat similar to how Z looks, and it looks also somewhat like inverted thing of what the probability. But the point is I can figure out the internal energy of my system right from that as well. Now, that is okay in a way. That works. Now, the next thing which I would like to do, but don't have time to do it today, is that I want to know what is the entropy of that system. Because that is something which we could not measure before. Internal energy is okay, energies have to be measured, thermodynamics knows everything about energies, that's fine. But entropies, that was in thermodynamics just something which you needed to multiply with the temperature in order to get something working there, so that thermodynamics continue to look symmetric. Internal times extensive times intensive variable. But nobody had an idea what that entropy was. But here now, we might be able to calculate, and that's what we're going to do on Friday. So, again, the homework for you is get an Excel file, which just looks like my Excel file, with the only caveat that your molecule has one fluorine over it. And so this coplanar ring pair here counts double in energy, should be put so. And these ones count single. The other thing which you have to realize is if you have the fluorine over here, it's not in the middle, it's over here. Lots of symmetry of the molecule is broken. The left-right symmetry is broken, the up-down symmetry is broken, there are lots of symmetries broken here. So there are actually way more states than they are otherwise. So we have way more configurations of different energies. So do that. There's also a warning, on Friday, I'm going to work more on my Excel file. And then, as an exception, there will be a homework from Friday to Monday. And that will be the same kind of homework I'm assigning now, that you please put into a new Excel file, or starting out from the previous one you had, whatever I do on Friday. So there will be a Friday to Monday homework. There will be, I think it's homework 9 then. Homework 9 will be from Friday to Monday, and it's just the same kind of thing. Whatever I do on Friday session, get that into the Excel file. And you guys get that. Okay, thanks so much.